Guys, I want to share with you the rest of the lab. We did not finish uh, yesterday. We finished first part, but then we have an emergency. We have to leave the lab because there is a fire alarm or something went off, so we have to leave. But I want to share with you here the. I want to share with you here the OBR2. Remember this Lewis dot structure of it here. The Lewis dot structure of it, as I mentioned that for you guys. We said we have two lone pair. Two sets of lone pair here, and we have PR, and we have PR. So we have two lone pair. This is one zone here. Let me switch color here so you can follow me here. So this is one zone. This is a second. This is a third. This is a 4. Correct? And if you look at this, this is A. That's my central atom. I have B. That's a terminal. A, B2. And then I have two lone pair, E and E. So E2. So this is, we say this has to be polar, correct? And from the code here, this is, from the code here, this is, it's bent, correct? And this is polar because of, you have lone pairs, correct? The presence of lone pair on the central atom will cause this polarity. And bent, and because it's bent, the angle is around 105 degrees, 105 degrees. The same time like H2O. All the time. If you have a lone pair on the central atom, you can expect this molecule will be polar. And the more lone pairs you have, the smaller the angle and the higher the polarity. So we did H2O and ammonia. Ammonia has one lone pair. H2O has two lone pair, which is more polar. H2O is more polar. Yes, and less angle. So ammonia has without lone pair is 109 degrees tetrahedron. Then you introduce yourself to ammonia, one lone pair, 107, from 109 to 107. You introduce yourself to this two sets of lone pair. This is 105, so it's squeezed. Now, can you imagine what will be if we have three lone pairs? If we have three lone pairs, what will happen? It will be less than 05, will be maybe 104, 103, 10 something, 102, something like that, correct? And by the way, those angles is done by the, as I said, done by the experiment. Those are X-ray crystallography here. So you determine those angles by experiment, not by calculation or something, theoretical calculation. No, by experiment. So now I'm showing you here, those are the two lone pair, correct? And here is my two bromine. The two bromine is here, see here? And the two lone pair are here. So this is AB2, E2. And according to the code table, this has to be bent. And the angle is similar to H2O. It's 105 degrees, correct? I want you to make a picture of this and add it in the column where it says Lewis dot structure. In this column, you divide it in two. You Google the Lewis dot structure from the web, and you have to confirm it with your own lab, results, which is this here. As I said, if you don't add the image, then I'll determine that you have not done the lab. So I'll take some points. So those are 5. Those are 5. And you divide the 5 over 100, that's 20 points for each image. Are you following me, guys? That's the way we are doing the lab. So now, let me go for the third. We have third, fourth, and fifth. So let's go for this. The next one. The next one is, as you can see here, So PCl3. So I'll make so we have PCl3. If you look like this, P C chlorine, 3 chlorines, correct? There's another chlorine, and remember phosphorus is in the 5A group, or 15 group, in the 15 group or 5A. I like to use both, but 5A will tell me it has 5 valence electrons. So that's phosphorus, 1, 2, 3, and 4, and 5. Now I know it has 1 lone pair set, and the chlorine has 7. Here is 1. 1 is here. 2, 2, and 2, and 2, 7. Here is 1. 1 is here. 2, 2, and 2. And here's the same thing. So chlorine is 7A or 17. So it has 7. So according to the first, we'll calculate our total VE. What's the total VEs? Phosphorus in 5A. So it has 5 VEs, valence electrons, correct? Chlorine, 3 of them, 3, and in this is 7A, by the way, multiplied by 7. So this is 21 VEs. So total how many? 26. Thank you. 26 VEs. That's the total. Correct? Now, after the total, we have to look at the code. We have to figure out the code. Let me switch color here so we can see the code here, guys. This is A. This is B. A central. The B's are terminal. And this one is E. So the code is A, B, 3, E1, 1 lone pair. So according to the code table, AB3E1, this will be correct trigonal pyramid. Correct? Is it polar or non-polar? What do you think? It is polar. That's because the polarity, polar. Correct? So we covered everything. How about the zones? How many zones we have? I can add, let me do here, change the color here. I can add those 2 together. That makes 4. Correct? But I can do here 1, 2, 3. 3 single bond and 1 lone pair, that's 4. We treat them as equal. So as equal zone or region or unit. So we have 4 zones or 4 regions or 4 units. So now I have to make up the real shape with the models here. I have 1 lone pair, correct? And I have 3. So this is, guys, look at this. 1 lone pair, and there's 3. All those 3 here, look at this. You look at them. Those are 3 chlorine. So 3 chlorine, guys, 3 chlorine, and 1 lone pair. That's trigonal pyramid. Trigonal pyramid. What it means, trigonal pyramid, means the base of this pyramid is trigonal, correct? Triangle, correct? It's trigonal or triangle. So that's a pyramid, which is modified from the tetrahedral. Tetrahedral, we don't have lone pair. The angle is 109. This one here, one lone pair, 107. So if we have 2 lone pairs, it will be 105. Okay, let's make a picture of this and add it to the Lewis dot structure column at the bottom of the Lewis dot structure. As I said, you have my permission to Google the structure and then put it there. Just minimize it and put it there. Okay, guys. So, any question about this? We'll take the second one for this second part. Any question? We calculated the total. So let's take the second one. The second one, we can look into the whole thing and look at carbon and 2 sulfur. Carbon has 4, correct? And sulfur has 2. This is carbon disulfide. Carbon disulfide. So the carbon, I'll put this carbon here, guys. The carbon here is carbon in the middle, and sulfur is here. So you have 1, and carbon has 6, 2 here, 2 here, and then here 2, 6. Okay, so and then here, and carbon has 4, and here is sulfur. So now if you look at this, what you can tell, do we have a lone pair here somewhere? No, we don't have a lone pair. So this will be, then the code will be, guys, will be A, B, B. There is no lone pair. This is A, B. The code said AB2. How many zones we have? We have 2 double bonds, 2 zones, correct? You can just look at the, as we said here, look at this one here. This is 2. So we have then, because of the 2, we have here 2 zones. We have 2 zones, correct? And how about how about the shape of this? The shape is, according to the code, we have to go to the table. This will be what? Linear. And the angle of the linear is 180 degrees, correct? Now the question is, it is polar or non-polar? What do you think? Non-polar, why? No, lone pair is not there, but it can be polar, correct? So how we can say that's non-polar? Because this one here, those are 2 B's, the same, similar. So the electronegativity is canceling. I mean, the dipole will start from here. So although they are the same, there's no dipole. I think it's this 2.0 and this is 2.0 something, or 2.3, and this 2.3. So the electronegativity difference is 0, and the electronegativity is 0. So they are non-polar. So we cannot draw any 2.3 or whatever. So they are similar to the electronegativity scale. Yes. The lone pairs is a different story, but we have to look at the electronegativity scale. I'll show you in a minute how we can look at the scale. Okay, I'll show you. Let's finish this, and then I'll show you the scale. If you have a difference in electronegativity, you have dipole, you have polarity. So if you have, I'll show you in a minute. Let's finish this one here, then I'll show you how we can change this one here. Let's look at this. So this is non-polar, correct? Non-polar. Yes. Yes. No. That's a double bond. You have a double bond because the octet rule has to be held for carbon, for 4 elements: carbon, nitrogen, oxygen, fluorine. They have to have 8 VEs. They have to have 8. Now, no angles. That's 180. This is a linear. That's a linear. No. I'll show you. Just bear with me. Just bear with me. What is the total number of valence electrons? Sulfur is 6A. 6A group. This is 6A. So you have 6 VE, and this is 6 VEs, and carbon is 4A. So it has 4 VEs. So how much do we have? 6 plus 6 plus 4. So 6 plus 6 plus 4 makes 16. Oops, sorry. So I don't know how to. No, it's just, this one is so sensitive. Whatever you do, it's just, and still not going anywhere. Okay, so now, so this is 16 VEs total. Those are 16 VEs total. Now, what is the questions I'm responding to you guys? Whatever you did not the correct shape. Let me show you here first about the polarity. Guys, let's look at the polarity here. Let's look at the polarity here. And so I have compared this, guys. Well, that's so compare those here. Carbon, this is S, correct? Compare this one here with OS. Guys, I'm replacing here, guys, listen. I'm replacing the oxygen here, the sulfur with oxygen. This one will be polar or non-polar. This is not polar. This one is polar. Why? Well, it turns out to be oxygen is more electronegative than chlorine. We'll start this one way here. This one, they have the same electronegativity. Electronegativity difference is 0. So the molecules will be polar towards the oxygen. So electronegativity is determined by the electronegativity. I mean, the polarity is determined by electronegativity differences between the whole thing. This is polar, but this one here, this is 0 difference. This is 0 difference. So therefore, what will happen here? You have 0, correct? Now compare this one here, guys. This is polar. This is polar within the bonding itself. So this is 3.5. This is I think we said what, 3.2 or something, or 2.5. I'm not sure, but say 2.5. And this is 3.5. So you see a difference here. There is a difference here. So there is a dipole pulling this one here. There's a dipole pulling. So within the compound, those are within the compound itself. We have 2 dipoles. However, those 2 dipoles are what? They are the same strength, opposite to each other. The same strength. So they cancel themselves out. The same amount. They cancel themselves out, and the CO2 here is said to be non-polar. But it has non-polar, but this is polar here. This bonding here by itself is polar. This bonding by itself is polar. But the net polarity is 0. Why? Because they are the same strength, opposite. But as soon as I get this one here out of my way, I put sulfur here, then the whole polarity will go this way. That's polar common, because, and that's the reason we said we don't have to have similar terminal atoms. So if you have similar terminal atoms like this and this, the polarity will be, net polarity will be 0. Okay, guys. So let's take this. Let's do the structure, guys. This one here. Okay, so and that's what most of you did not really realize. That's not correct, because we are dealing with not. We are dealing with linear. So the one that has double bond, smaller one, double bond, and you have a sulfur here. Take, just bear with me a little bit. Here, guys, can you see it? Can you see it? That's linear. In the middle is your carbon, and the sulfur is the other side. Although the sulfur is bigger than carbon, but I did not find. Maybe this is not good resemblance. Let me take the bigger atom here. Guys, here I changed just the size. Sulfur is bigger, so here it is. Can you see it? Here it is. That's your carbon. That's your sulfur here. Those are sulfur here, correct? There is no lone pair, linear, 180 degrees. Everybody's looking. So make a picture of it and upload it to this CS2. CS2. Okay, guys, this is CS2. This is carbon. Those are two sulfur, and then 180 degrees. So I take the last one. And the last one here, we did this one here before, but we need to see the model of it. So you can start doing the model. We did this one here together, if you remember, but let's do it together here. So this is the chlorine is here, and you have the carbon is in the middle. Chlorine, and chlorine. So you have 7 for chlorine. We have 7 valence electron for chlorine here, and carbon is 4, so we have 7 here. Okay, guys, 7. So then we have to go through the calculations. We calculate first our zone. This is A, B, 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 and B. So this is A, B, 4. This is AB4. There is no lone pair on the carbon. All the carbon is bound by the 4 single bond, AB4. And if you look at the AB4, this is 4 zones. 4 how many? Zones. Now you can tell this is 4 single bond. 1, 2, 3, and 4. So out of this, we can determine that is tetrahedral. And we know that the tetrahedral angle is 105, no lone pair, 105 degrees. Now, it is polar or non-polar? What do you think, polar or non-polar? Although we have 4 dipoles, we have 4 dipoles. This dipole here, let me show you here. Let me show you here. This is, we'll pull this way because chlorine is more. This here, that's the start of this, is this here. We'll pull this way. Start here, we'll pull this way. This start here, we'll pull this way. We have 4 dipoles. We have polarity within the compound. However, those polarity are the same strength, opposite direction. They cancel themselves out. And this is called to be, because of the same thing here, is non-polar. The net polarity is non-polar. So this is non-polar. You have 4 dipoles within the compound. The polarity is present within the molecule, but then when you have the whole net about the whole molecule, those 4 dipoles, they are canceling themselves out. The same strength, opposite direction. Same strength, opposite direction. So the net polarity is 0. And that's the reason we said if you have equal terminals, then you can expect what? You can expect this one to be non-polar. Now, can I make this one polar? Yes, I can make this one polar. I can do this one here. Look, guys. This chlorine, and the 4th one here, I say fluorine. So I displace one of the chlorine with one fluorine. So I have 3 chlorine and 1 fluorine. This is polar. This is polar. This is polar because they are not equal strength, correct? The polarity is not equal strength, not canceling themselves out, and therefore the terminals are not the same, not identical. So there is a difference in electronegativity scale. Yes. Yes, yes, electronegativity. Fluorine is fluorine atom said to be the highest, and I'll mention in a minute. So I'll share with you the whole thing. So let's build this one here, the last one, please, and then we'll go for the electronegativity because I think you have issues with the electronegativity, and I hope everybody will get this one straightened out in your lecture. So um, this is tetrahedral, guys. I want to make sure that's a tetrahedral. Okay, so one, those are single bonds, guys. 1, 2, and then 3, 3. All those the same length, single bond, 3, and 4. So, and then I'll say for the chlorine, this carbon here, fluorine is bigger. So I'll make it this one here so you can see 1, 2, and 4. Okay, guys. May I have your attention, guys? Look at this. This is your carbon, and this is your 4 chlorine, correct? So 1, 2, 3, 1 in the top. This is a tetrahedral. If you put it here in your hand, okay, this is a tetrahedral one. Can you see it? This is a tetrahedral. 1, 2, 3, 4. 4 chlorine and carbon in the middle. That's a tetrahedral one. Can you see it, guys? This is 4. That's a tetrahedral. And the angle is 105, no lone pair. If I introduce one lone pair, it will drop. Trigonal planar, and it's 107. If I introduce 2 lone pair, it will drop to 105, like H2O. So the angle will be suppressed even further. So that will conclude the whole lab today. Make sure that you make an image of this. Make sure you make an image of this. We have plenty of time, and I want to go through the electronegativity. I want to go through electronegativity. Just bear with me 10 minutes for electronegativity. Don't leave, guys. Don't leave. Don't leave. So here it is. Let me share with you here. Okay, guys, you have everything. Oh, did we calculate the amount? We did not calculate. Let's hold on, Hold on, guys. We did not calculate the total BEs. How many total BEs? Somebody will tell me. This is 7, and this is 7. This is 7, and this is 4. This is 21. 3 multiplied by 7 is 21. 21 plus no, 3, 4, sorry. 4, 7, 28. 28 and 7 multiplied by 4 plus 4. This is 32. 32 total BEs. Okay, guys? Okay, so let me take this one out. And let me share with you here. Let me put the Google here or Bing. So bear with me, guys. Electronegativity worksheet, guys. Okay, guys. Listen, guys, please, guys. So, electronegativity and polarity problems. So let's look at this, see if we can get something out of this electronegativity. Okay, so it gives us the Cl2CO. L2CO. It is polar or non-polar. How I know this? No, no, the first compound, guys. Why is polar? You said polar, why? How I can know this? I have to go through drawing the Lewis dot structure in order to know the polarity. You have to go through what? Guys, listen, listen, listen. Would you stop, please, talking in the back? So we are looking at this. We are looking at this compound here. Here, guys, please. I know you have different lecturer here, professor. So Cl2CO. How I know this is polar or non-polar? I have to draw the Lewis dot structure. So you can tell this carbon is the least electronegative, will be in the middle. This is oxygen. This is, that's yes, you have to look at the chart, at the periodic table. You have to look at the periodic table and see which is the most electronegative. In general, electronegative atom is always put at the edges, terminal. The least are here, least here, least electronegative. So, guys, in the back, could you just 1 minute, 1 minute? I know you have a different structure, different professor will teach you different, but I'm teaching you the correct one. So here it is. Carbon is the least, 2.5. Chlorine is 3.0. So this is about 3.0. This, I think, is 2.5 something. So there is a difference. This is 3.0, and all of them 3.0. This is 3.5, the highest, 3.5. This is 3.0. So this is 2.5. There is polarity there present. Why? I can take this one here. Well, where is the most electronegative one? 3.0. The chlorine is more electronegative, so the dipole will start pulling electron of valence electron of carbon this way, and the other one from here this way. And here 3.5, 2.5, the oxygen is more polar, will pull this way, the 2 electrons here. So this is polar. However, the polarity itself, because those are the same strength, the same molecule, those will cancel themselves out, most probably. They are identical, correct? They are identical. Okay, they are identical and opposite direction. One goes this, one the other way. However, this one here, predominant. So this is 2.5, 3.5. The net of the whole thing is 1.0. It's polar. So this is polar because this is 3.5, this is 2.5. Correct? Pick up one more example. Pick up one more example, please. So pick up one of those. And the answer A, let's look at the answer. What is it? Predict the compound. It's a covalent, but what is a covalent? Because you can predict from the polarity whether it's polar or non-polar. So there is a table there according to the scale of according to the scale of electronegativity. If electronegativity difference, guys, we came out to be what, guys? We came out to be, it is. The difference is, we said, how much is it? Come on, guys, you let me down. You tell me, you let me down here. So this is 3.0, 2.5, 3.0. We said those are this way here, canceling themselves out. So we're not consider this. This is 3.5. So 2.5 to 3.5 is what? The difference is the electronegativity difference, delta electronegativity N. 3.5 minus 2.5, how much is it? Around 1. Then you have to go inside your table. We don't have it in the lab, but that's the lecture for. So table will tell you from 0, delta En, the electronegativity difference, from if it's 0 to 0.04, correct? That's covalent nonpolar. Covalent nonpolar. Okay, guys. Now, if I will say, I have to stop sharing because I think it might not take the. I have to get out of the. So let me. I apologize. So let me stop sharing, and it's so cumbersome with this WebEx. So now it's sharing. So we said about this compound here. Let me see here. So here it is. So we said about this compound here to be, we have chlorine. Here it is, chlorine. And we said it's 3.0, 2.5, 3.0, and 3.5. Correct? So that's electronegativity. Electronegativity. So E, electronegativity. So we said those two here will cancel themselves out because they are the same. So this one here is the difference between them. The difference between them here, those are the same, so they cancel themselves out. The only predominant is this, which is 3.5 from oxygen minus 2.5 from carbon is 1.0. Okay, guys. Now you have to look at the scale. The scale will tell you from 0, that's delta electronegativity difference, electronegativity difference here. From 0 to 0.04, this is covalent. The type of bonding is covalent, and it is nonpolar. It is what? Nonpolar. From 0 greater than 0.4 to 1.8, correct, or 1.9, this is polar, what? Covalent. Covalent. Now, then greater than 1.8 or 1.9, this is ionic, correct? So you can tell we have one is this compound here, the Cl2CO, this compound here, COCl. This is covalent and it is polar. So you have to know this here, this table. Yes. Which one? From 0 to 0.4, that's covalent nonpolar. Nonpolar. The scale is in college. He is not in our class. But they did not give you the polarity. The question is, predict which one of the following around the covalent bond will be polar. So it does not give you, it's asking about polarity, whether covalent, a type of bonding, covalent or non-covalent or bonding. But it's not asking per se, it's polar. So let's look at this, guys. You tell me about this. Somebody had opened the cobalt here, cobalt. Somebody had opened, let me take this one out. We have, this is, yes, 1.8 or 1.9 is polar. Is above this will be ionic. From greater than 0.4 to up to 1.8, or some textbook will use 1.9. From 1.8, 1.9 to 1.8 to 1.9 and above, that's ionic. Between greater than 0.4 to 1.8 or 1.9, that's covalent polar. From 0 to 0.4, that's covalent nonpolar. Was that? Yes, yes, yes. So now you tell me about this one here. So I'll take one example here. So here it is. NCl3. That's polar or non-polar. So do the just N, Cl, 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 and then one. Okay, you don't have to calculate, but you can calculate. You can calculate. This is polar. This is polar. Nitrogen is greater than chlorine. So all this pulling will be this way, same direction, and the whole thing this way. So the net. So, and that's the reason we say all the time you have this, you have a lone pair there, it has to be polar, but you can calculate. No value, no value. But you have three the same direction. Okay, guys? So you can look at the three in the same direction. So guys, I'll stop here. I'll stop recording so you can just look at the whole thing here. And okay, I'll stop recording, and I hope if you have any question, you can still meet with me and WebEx with me anytime. I'll stop